All right, so let's see. Okay, so good morning, everyone. I guess it's morning in Singapore.
怎么办？怎么办？
Are you guys able to hear me?
Yes, I can.
Okay, good. All right, thanks for the confirmation. So now I can move along. So welcome back to EE4210. So last time we were looking at principles of reliable data transfer, and then we got started on TCP. So I'll do a quick recap of what we did on Friday, and then we will move on to the rest of the topics in TCP. So for example, today we will cover things such as the reliable data transfer, flow control, connection management, and we'll also try to do TCP congestion control. Okay, so quick recap. So last time we were talking about reliable transmission, and here we saw that if we want to recover from losses, what we need to do is one thing is I want to know if the receiver has received my packet or not. So so we have to have the notion of acknowledgements. So if the receiver receives any packet I send, the receiver is supposed to send an acknowledgement. Also, in case the receiver does not receive my packet, it will not send any acknowledgement. So what I also do is I keep a timer with every packet I send. So if I don't get an acknowledgement within the timeout period, then I will retransmit that packet. So this we saw was basic stop and wait. And last time we also saw that sometimes we can run into problems if for example, if the acknowledgement comes after okay. Somebody is, okay, that's fine. Somebody is trying to do closed captioning. That's okay. Let's see. Let me close this. All right. If the acknowledgement is lost or if the acknowledgement comes after the timeout period, then we run into problems. And and here the problem is that we don't know if the receiver is acknowledging a new data packet or an old data packet. And there we saw that we can solve this problem if we add sequence numbers to the packets and the acknowledgements. And last time we also saw that it is necessary for the acknowledgements to also have a sequence number. Otherwise, it doesn't work. Then we looked into the performance of this stop and wait protocol, and we saw that while it performs the necessary, it satisfies the requirements of reliability, the performance is not very good. So the utilization of the link is actually pretty bad. So then we saw that we can improve the utilization by allowing more than one packet to be sent while waiting for an acknowledgement to come in. And this is what we call pipelining. And then we saw two specific examples of pipeline protocols, go back N and selective repeat. So in the main idea about go back N is that I'm allowed to send a window of packets, and then I have one timer running. And in case there is a loss, I will retransmit the loss packet as well as anything else that remains in that window. And at the receiver, we do cumulative acknowledgements. And if we get packets in order, the receiver will keep those packets. In case there's an out of order packet, that packet is discarded and we resend the acknowledgement with the cumulative. So we acknowledge the highest in order packet received so far, right? And one problem here was that whenever there is a, when the timeout occurs, everything in the window is retransmitted, even though they were received correctly previously. Now, in order to avoid such an inefficiency, we have the notion of selective repeat. Here, again, the sender will have a window. It can send all the packets in the window, but at the receiver, even if there's an out of order packet, it is saved. And when we send acknowledgements, each acknowledgement packet corresponds to one specific packet that was received. So it's not cumulative anymore. So you get packet number N, you acknowledge packet number N. If you don't get N plus 1, but you get N plus 2, you can acknowledge N plus 2. And every packet here has its own timer value. And if a packet timer expires, then we retransmit that only one packet, that specific packet. We don't have to retransmit anything else. So it's a bit more efficient, but then this is a little bit more complicated at the receiver. The receiver has to maintain, out of order packets. The sender side is also a bit more complicated because now we have a timer for every packet. Right? So the implementation is a bit more complicated. Right. So after this, we started looking at TCP, and then we looked at some basic ideas of TCP. For example, it's reliable, it's pipeline, it's full duplex, it's a connection oriented, and it provides congestion control as well as flow control. Then we also looked at the structure of TCP packets, and then we were talking about how sequence numbers are used and acknowledgement numbers are used in TCP, right? And then we looked at one specific example of telnet. So now what I will do is, before we move into this reliable data transfer, what I'll do is maybe we'll have another look at how sequence numbers and acknowledgement numbers are used in TCP, just as a, to brush up, as well as to give us a little bit more idea about sequence numbers and acknowledgement numbers. All right. How do I, let's say function W, yeah. Okay, so now let's try a couple more examples of sequence numbers and acknowledgement numbers. So let's say I have a sender and I have a receiver here, or a client and a server, whatever you want. Let's say at this side, at the client side, this is the server side. Let's say at the client side, I have sent certain number of bytes already. So let's say I have already sent 100 bytes from this side, and the server has sent 75 bytes so far. Now we get a new packet, and that new packet has 20 bytes of data. So now when I send this particular packet, if you look at the sequence number, I have already sent 100 bytes. This new packet has 20 bytes. The starting point of that is 100, right? So if you think of your things like this, you have already sent up to 100. Now you have another 20 bytes of data. So you're going up to 120. But if you look at the first byte of this packet, that is byte number 101, right? So the sequence number here, we have already sent up to 100. So the new packet, the sequence number will be 101. And at the same time, we will also acknowledge what we have received so far from the other side. So far, we have received 75 bytes. So the acknowledgement here will say, give me byte number 76. Okay. So now when the receiver gets this particular packet, it will send an acknowledgement. Right? In this particular acknowledgement, the sequence number is 76. Whether we send any data or not, the sequence number will be 76, indicating that the next byte we send will be byte number 76. And when I look at the acknowledgement field, this guy has now received 100 and another 20 bytes. And the packet started at 101 and it had 20 bytes. So you have received up to 120. So the acknowledgement will say, I have received up to 120. Now I'm looking for 121. Now, if now there's another packet, and let's say this time we are 50 bytes. So now you will send the next packet, and that will go up to 170. And the first byte here will be 121, right? So here the acknowledgement, the sequence number of this packet will say, I'm starting at byte number 121. And from your side, I have still only received 75 bytes. So I'm still looking for 76. And if we get this packet correctly, then the receiver will send a packet. And here, maybe it doesn't have any data to send. So the sequence number will still say 76 because that's, if I were to send any data, the sequence number will be 76. But now I have received up to 170 from your side. So I am looking for byte number 171. Right? So the acknowledgement will increase to 171. Okay. So hopefully this gives you some idea about how, additional example of how sequence numbers and acknowledgement numbers are increased in response to packets being received. Okay. Any questions from anyone? You can either speak up or you can also type in the chat, depending upon whatever you're comfortable with. So any questions? Let me make sure that I'm actually recording. Yeah, it's being recorded, so that's good. All right, so in case there are no more questions, so maybe I'll move to the next one. All right, so now let's get started with today's topics, right? So let's look at how TCP does reliable data transfer. Okay. And again, just to quickly recall, the transport layer protocol here is the transport layer protocol that we have here is TCP, and below TCP on the network layer is IP, right? And IP itself is unreliable. So TCP tries to create reliability on top of this unreliable network layer and the data link layer and so on. So before we get into TCP, so let's look at now, whether TCP is pipelined or stop and wait or go back N or whatever, right? So it turns out that TCP uses pipelining. So it's not a stop and wait protocol. TCP is allowed to send more than one packet at a time. However, in the two examples that we have seen previously with go back N and selective repeat, the number of packets that you can send, let's say N, is fixed, right? We decide in the beginning whether we can send 5 packets or 10 packets in the window. With TCP, we do use pipelining, but this value of N is not a constant. It keeps changing with time. And it changes depending upon whether we have congestion in the network or not. So towards the end today, we will see how this N changes in TCP. All right. So now, when we were talking about go back N and selective repeat, we saw that one uses cumulative acknowledgements, the other does not, right? And in TCP, we have seen so far uses cumulative acknowledgements. So it sort of seems like it is picking up more towards go back N, right? But it's not exactly go back N, as we will see in just a bit. Also, another similarity with go back N is that there's a single retransmission timer. Only one timer is maintained. We don't have a timer for every packet. If you want to maintain a timer for every packet, that's more expensive in terms of computational resources that you require. Okay? So only one single timer. However, we will soon see that, in go back and remember when there was a timeout, we retransmitted every packet after that lost packet, right? We retransmitted everything in the window. In TCP, we don't do that. When we retransmit, we only retransmit one packet, and we'll see. And another difference compared to your traditional go back and or selective repeat is in go back and selective repeat, when we have a retransmission, that's triggered when there's a timeout. In TCP, of course, we can have timeouts, but we can also have one more way in which we detect a possible loss in the network, and that is using duplicate acknowledgements. So this we have not seen earlier in either go back N or selective repeat. So this is something new with TCP, and we'll talk about this. Okay. So rather than jump into everything in one go, let's start with a very simple TCP sender. Okay. So we will not worry about duplicate acknowledgements for the time being, and we will also ignore things such as flow control and congestion controls. This will come slowly. So let's just look at how TCP will handle losses in the network, and then we'll worry about flow control and congestion control. All right. So this is what your typical TCP sender will look like, right? So let's imagine, or not imagine, right? Let's look at what a TCP sender will usually do. A TCP sender will receive data from the application upper layer. When it gets a piece of data from the application, it will create a packet with the proper sequence number, right? And as we have seen, the sequence number is the number of the first byte in that segment. So it's the byte number of the first data byte. Now, if you already have a timer running, that means you have previously sent data packets and you're waiting for an acknowledgement. In that case, you can just send the packet if it is allowed. Otherwise, you start a timer. So in TCP, what will happen is you have only one timer, and that timer is associated with the oldest packet that is not yet acknowledged. Right? If there's already a packet you have sent and there's a timer running already, so for the new packet, you don't have to start a new timer. Only one timer at any given point in time. Okay. So this is what when you receive data from the application. What if you receive an acknowledgement? If you receive an acknowledgement, if you look at the sequence number in the acknowledgement, if you have already seen that same sequence number earlier, you don't have to do anything, right? It's a duplicate acknowledgement. It's not moving your, if it is the same acknowledgement number as you have seen before, no need to do anything. You can ignore it. But if it is acknowledging new data, you should move your base to reflect that new data has been acknowledged. And new data has been acknowledged. Are you still waiting for more data to be acknowledged? In that case, you need to restart the timer, right? So we only have one timer, and that's always associated with the oldest unacknowledged packet. And what if you are waiting for acknowledgements and you never get acknowledgements? Then at some point, you will have a timeout. When there is a timeout, you retransmit that particular packet, the oldest packet. Right? So the timer is always associated with the oldest packet. That means the first packet in your window, that's the oldest packet. So when the timeout happens, you retransmit the first packet in your window, and then you restart the timer. So now you can again wait for the acknowledgement to come in. And you only retransmit the oldest packet, the first packet in your window. You don't retransmit the rest. Okay? So let's look at how this operation happens, just to illustrate. Right? So let's say we have two hosts, A and B, and A is sending packets. So let's say we have so far sent 91 bytes of data. Okay? So far we have sent 91 bytes, and now we have a new packet, and it has 8 bytes of data. So if you already sent 91 bytes, so for the new packet, it will start at byte number 92, right? So the sequence number here will be 92. And what do we have? 8 bytes, right? So that's 92, 93, 94, up to 99, right? So these are my 8 bytes of data. So this packet contains these 8 bytes. So if this packet is received correctly, so the receiver receives byte numbers 92 to 99. So what is the receiver expecting next? The receiver wants 100. So when it sends back the acknowledgement will say, I am looking for 100. Give me 100. Okay. Now consider the situation where the acknowledgement is lost. So what happens? This is the only packet, let's say. So there's a timer value associated with it. So we are waiting for the acknowledgement. And at some point, the timer will expire. At the time, I will retransmit this same packet. And hopefully this time the receiver gets my packet, so it will send back the same acknowledgement. However, here, the receiver already has received up to 99. So this packet is duplicate, right? You are again getting byte number 92 to 99. So the receiver will throw away this data. It will not, give this data again to the upper layer, to the application. So the receiver knows we have already received this, so we don't need to keep this data anymore, so we can throw it. Right? So it's the simplest case. You sent something, the acknowledgement got lost, so after the timeout, you resend the packet again. So now let's consider something a little more complicated, right? So this is the situation with a premature timeout. So again, the same thing. So I had previously sent up to 91 bytes. So my base is at 92 right now. So let me let the ink stay for the time being. So I'm going to start at 92, and there are 82 bytes of data. So it'll still be 92, 93, up to 99. And this is my timer value. Okay. So now the acknowledgement is being sent. But let's say for some reason it took a long time in the network and the acknowledgement is delayed. So when the timer expires at this particular point in time, the acknowledgement has not been received. So host A thinks, oh, my timer expired, I didn't get the acknowledgement. So the packet must be lost. So it's going to retransmit, right? But in this case, let's make it a little bit more interesting. So let's say there is a second packet which was created here, and this had 20 bytes of data. So previously, the first packet was starting at 92, and then it had 8 bytes, right? So the next packet will start at 100. Next byte will be 101, and so on. Then 102, and it has 20 bytes of data, right? So it will go all the way up to 119. Right? So the second packet has byte numbers 100 to 119. Right? So now this is just to create a little bit more interesting scenario. So here, I send the first packet, then I send the second packet. The acknowledgement for the first packet is coming, but it's just delayed. At this point, my timer has expired. I have a timeout. So what will happen? I will retransmit my packet anyway. Right? I will retransmit my packet. However, when this acknowledgement comes in, this acknowledgement comes here. When this acknowledgement comes, the receiver doesn't know, or host A doesn't know, is it for the new packet or the old packet? But it doesn't care. All it cares is, oh, the receiver has received everything up to 99. It's asking for 100. So it's going to change its base now. So if I go back to my algorithm that I had here, we got an acknowledgement that acknowledges previously unacknowledged segments. So I'm going to update what is known to be act. So that is what it means here. So now when this acknowledgement comes in, I update my base to 100. And after a little bit, when this acknowledgement comes in, 120, I update my base to 120. I know everything up to 119 has been received correctly. However, since my timer had previously expired, I had retransmitted what I thought was a lost packet. So I retransmitted the packet with 8 bytes of data starting at 92. So at the receiver, this is again a duplicate packet. Receiver doesn't care. It will just throw away this packet, but it is still going to send an acknowledgement. But when it sends the acknowledgement at the receiver, we have received everything up till 119. So this acknowledgement will again say, give me 120. Okay? So even though the new packet started at 92 and it had 8 bytes of data, So that means from 92 to 99. As far as the receiver is concerned, this is an old data. So far, I have received everything till 119. So it will tell the other side that give me 120 now. Okay. Now let's look at an even more interesting scenario, right? And this is to show you what happens when there is a cumulative acknowledgements. Right? So let's say again, as before, I send 8 bytes of data starting at 92, and then I have a timeout value associated with this packet. Let's say the acknowledgement was sent, but the acknowledgement got lost, right? So if the receiver gets this packet starting at 92, 8 bytes of data, so it gets from 92 to 99. So it's looking for 100 at this point. So acknowledgement will say, give me 100. But if I send the next packet with 20 bytes of data that starts at 100, once this packet is received, the receiver will say, okay, just like in the previous slide, it has now received everything up to 119. So the new acknowledgement will say, give me 120. And in this case, we are lucky that the acknowledgement for the second packet came in before the timer expired. And here, because I got I don't have to get exactly this acknowledgement, right? I don't have to get something that exactly says I got 100. When I get 120, it implies that I definitely must have gotten this. Otherwise, cumulative acknowledgement will not go to 120. So in this case, this loss of acknowledgement has no effect on me, and I don't have to retransmit anything. So if I still have data available, let's say now I have another 15 bytes of data. So previously, the first one started at 92 and went up to 99. The second packet started at 100, went up to 119. And let's say I have still some more data. So that's at 120, and so this is 15 bytes. So that's up to 134. Right? So now I can send the new packet out, and the sequence number, the first byte is number 120, and then it will go up to 134. Okay? So the goal here is to say, with cumulative acknowledgements, one of the advantages is that even if I lose one acknowledgement, and if I'm lucky, and then the subsequent packets which were transmitted, the acknowledgement for that suffices for me to move my send base and not have to worry about retransmitting the packet. Okay. Any questions on these scenarios that we just talked about? Let me see if anybody is writing anything on chat. No. All right, somebody wrote something. Okay, so somebody says slide 42. Does this mean that if the first window fails to be dropped? Wow. Let me try to understand what this question is saying. So somebody says, does this mean that if the first window, or probably you mean the first packet, fails to be dropped? No, I don't think I understand the question properly. So it says, does it mean that if the first is lost in transmission? Okay, so there is a oh, no. Okay, so I think now I understand what the question is. Okay, somebody raised a hand. Did you want to ask your question?
Sorry, Prof. So
Yeah.
if sequence 92, as in because the acknowledgement is not back to host A, right? How does it know that is the sequence number 2 has been received by host B? I think.
Let me erase these guys here. Sorry, what's your question? So the first packet starts at sequence number 92, and it has 8 bytes of data, right? And what do you want to do? You say that this packet will not be received. Is that the scenario you want to consider?
Yeah, I mean, because if acknowledgement isn't received by host A, right, how does host A know that his transmission was received by host B?
So the first packet started at 92, right? And it had 8 bytes of data. In the question that you're asking, do you want to assume that this packet is received or not received in reality?
We assume as received, but the acknowledgement is not.
Okay,
right?
But the acknowledgement is lost, right? The acknowledgement didn't go through.
Yeah.
Right? So this acknowledgement, when it was sent, it would have said, give me 100, but it just that it was not received. Okay? Right?
Yeah.
If there is only one packet to be transmitted here, then nothing else will happen. At some point, there will be a timeout, and then you have to retransmit this packet now. Okay? However, in this situation, what we are considering is there were more data to be sent by the sender. So there is another packet which was sent immediately afterwards. And this started at 100, and it had 20 bytes of data to be in it. Now at the receiver, it acknowledged the first packet. It doesn't know that the network lost that packet. And the receiver doesn't care. So now, as far as the receiver is concerned, the first packet meant it has received everything up to 99, and we are good. The next packet comes in, starts at 100, and it has 20 bytes of data. So now I have received everything up to 119. And we send an acknowledgement saying, give me 120. If this acknowledgement is received, I don't care about the first one. If this 120 is received, at the sender, the host A to begin with, it knows everything up to 119 is received. And this is because we are using cumulative acknowledgements, right? And cumulative acknowledgement implies that we have received everything up to this. Now consider another situation, right? Let me do this. What if the first packet was not received? So this was 92 and 8. But the second packet is received. So this is 100 and up to 20. There will be an acknowledgement sent for this. But this acknowledgement will say, give me 92. Because so far, the reason I'm sending here 92 is I have already transmitted up to 91. And let's say up to 91 has been acknowledged. So in this situation, if the receiver does not receive 92 but receives 100, the acknowledgement will still go back and say, give me 92. Because again, we are doing cumulative acknowledgements. It only tells you up to this I have received. Beyond it, maybe I've received some, maybe I've received only 1 byte, 2 bytes, doesn't matter. Up to 91 has been received correctly, give me 92. And that's the reason when I get an acknowledgement saying 120, it implies that up to 119 has been received correctly. Does that answer your question?
Yes, Prof.
Okay. All right, let me see if there's any other question. Okay. All right, so then after this, we were talking about acknowledgements. Oh, sorry. We were talking about TCP sequence numbers and acknowledgements and so on. In real life, the way TCP acknowledgements work is a little bit more complicated. Okay? In our examples here, every time a data packet is sent, TCP will send an acknowledgement. In real life, that's not what it is. Depending upon what the situation is, the acknowledgement, the way we generate may be different, right? And the biggest thing is here, there is something called a delayed acknowledgement. And that basically says TCP does not have to send an acknowledgement for every packet immediately. let's look at the motivation for this, right? In general, what we do, every time we get a packet, we should send an acknowledgement, right? Now, usually, if in a typical, when you're trying to download something, the data is only coming in one direction, the acknowledgements don't have any data. So if you send an acknowledgement for every packet that you get, you're just inserting 40 bytes into the network, which is just serving, it doesn't have any real data, it's just serving the purpose of an acknowledgement. And while now we may have very high speed internets, at home you can have an optical fiber that can give you 1, 2, 3 gigabits per second. In the old days, the networks did not have so much capacity. So the designers felt that acknowledging every packet just introduces too much overhead into the network. So it said, let's not acknowledge each and every packet. Rather, this is what we do. If you get a packet, don't acknowledge immediately. Wait for some time. How much time? That's your 500 milliseconds, right? Half a second. So you wait for a certain amount of time. If you get a second packet within this interval, then you send the acknowledgement immediately. So for every 2 packets, you send 1 acknowledgement. And the reason for doing this is the number of acknowledgements in the network are reduced by a factor of 2. So you reduce the amount of overhead that you create in the network. Right? But then you also imagine that if I keep waiting for a second packet and that second packet never arrives, then I'm just not acknowledging anything, and the sender probably is not going to send anything more. So after this 500 milliseconds, even if you don't get this particular acknowledgement, right? If you don't get this particular packet, you don't delay forever. After this timer expires, you send your ACK anyway. Okay, so this is what this part is saying. So if you get, oops, sorry. Okay, so if you get a packet, crap, pen. You get a packet. It's in order. It's giving you the actual data that you were expecting. You don't immediately send the acknowledgement. You delay the acknowledgement. You wait for up to 500 milliseconds for the next packet to come in. If nothing comes, you send the acknowledgement anyway. You don't wait more than 500 milliseconds. On the other hand, if you get a packet, it's also in order. This is the sequence number you're expecting. There's already 1 packet that had arrived before, and you have not sent an acknowledgement yet. So now there are 2 packets, right? So in this case, you can immediately send a cumulative acknowledgement, acknowledging both of them. So this is, again, to illustrate. When the first packet comes in, you don't immediately acknowledge. You say, I'm going to wait for 500 milliseconds. If nothing comes in this 500 milliseconds, I will send the acknowledgement. However, if you get another packet coming in within this 500 milliseconds, you send back an acknowledgement. And since this acknowledgement is cumulative, right? Effectively, so if this was starting at 92 and it had 8 bytes, and if this was 100 and acknowledging and had 20 bytes, your ACK here would say 120. And since it's cumulative, it serves the purpose of acknowledging this packet as well as this packet. Okay. And I have reduced instead of sending 2 acknowledgements, I only needed 1 acknowledgement. So this is basically the first 2 lines here. Now we also see 2 other special cases. Right? What if I get a packet, but it is out of order? This is not in the sequence that I was expecting. In that case, you immediately send a duplicate acknowledgement. No, you don't have to wait. So let me illustrate what I mean here. So this is this situation. Let's say on this side, you have received everything up till byte number 91. Let's say for some reason you get a packet here that starts at sequence number 100. So you are expecting byte number 92. You have received everything up till 91. So right now you want 92. You get a packet whose sequence number is 100. This is not what you're expecting. This is higher than what you're expecting. In this case, you will send an acknowledgement immediately. And this acknowledgement will still say, I'm looking for 92. Right? So this is number 3 there. And what if you get a packet that partially or completely fills the gap? In that case, you will immediately send an acknowledgement. You don't have to wait. Okay? If you get a packet that fills something that you are expecting, then you can immediately send the packet, send the acknowledgement. So these are different different cases, and there is a reason why we do this. And the reason is the way TCP figures out that there's a loss. There are 2 different ways in which we figure out there's a loss. One is, of course, when there's a timeout, and then there's another thing which we use duplicate acknowledgements to indicate that there's a loss. So that brings us to this fast retransmit. So let's try to understand what fast retransmit is. Okay, so let me again draw something to illustrate fast retransmit. Oops, this didn't come out as a straight line. All right. So let's say we are sending a window of packets. This is the first packet. Let's say the second packet doesn't make it, third packet, fourth packet, fifth packet, sixth packet, and so on. Okay? So let's say I sent 6 packets in a window. And let's give them some sequence numbers. So maybe we'll just make our life easier. So let's say this starts at 90, has 10 bytes of data. This started at 100, also has 10 bytes of data. The next one will start at 110, has 10 bytes of data. This started at 120, has 10 bytes of data. I got how many? 1, 2, 3, 4. So the next one will start at 130, has 10 bytes of data. And the last one starts at 140, has 10 bytes of data. Right? So these are my 6 packets that were transmitted. All right. However, now 5 of them made it, and then the last one didn't make it. Oh, sorry, the second one didn't make it. The remaining 5 made it. So let's look at how the acknowledgements will look like, right? So when the first packet is received, the byte number starts at 90, and then there are 10 bytes in it. Okay? So if I look at it from the point of data, at the receiver, you have from 90 till 99, right? You have received this. So what are you looking for now? You're looking for 100. So when the acknowledgement goes back, it says, give me 100. Now the packet with actually that started at 100 was lost in the network. But you get a packet that starts at 110, right? This is not what you're expecting. This is higher than what you're expecting. So what do? You send back an acknowledgement, but it still says, I'm looking for 100. Now, that brings us to another question, right? So now I got like this, starting at 110 up to 119. This is out of sequence. In go back N, I would have thrown away this packet. We don't keep out of sequence packets. What about TCP? Should I keep? Should I throw? It turns out that if you look at the TCP standards, the standards don't say anything, whether you should keep or whether you should throw. So if you are the operating system developer, whether you're writing Linux or Windows or whatever it is, so it's left up to the implementation. You can choose to do whatever you want to do. You want to keep, you keep. You want to throw, you throw. And most operating systems will keep the packet because it's a perfectly good packet. Why do you want to throw it away, right? Otherwise, the network will have to retransmit later anyway. So most operating systems these days, even if you get an out of sequence packet, it will store it. It's just that, it will not give it to the application yet because we are missing some data. So again, so in this case, the receiver will store byte number 110 to 119, but the acknowledgement will still say, give me 110. I'm sorry, give me 100. So now the next packet comes in, and this starts at 120 and goes all the way up to 129. Again, this is out of sequence because I'm still waiting for 100 to come in. So the acknowledgement for this will still give me 100. The next packet comes in, it starts at 130, has up to byte number 139. This is still not what I want. I'm still looking for 100. So the acknowledgement here will still say 100. And the last one, which is 140 up to 149, the acknowledgement for this is still going to say 100. Right? So this is how it's going to be. And this is the oldest unacknowledged packet right now. So let me use a different color. So let's say there's a timeout value here. So this is my timeout. And when this timer expires, at this point, I will retransmit packet beginning with 100 has 10 bytes in it. Now, usually what would happen is this timeout value is pretty large. Right? So you have to wait for that, maybe 1 second, maybe 5 seconds, something. You wait for the timer to expire. So it turns out that that can be pretty inefficient. So you have to wait for a long time before your timer has expired and then you retransmit. But if you look at what was happening here, and maybe I use a different color, maybe purple. Yeah. This was the first time you got an acknowledgement for 100. Then you get a second acknowledgement for 100. So this is a duplicate. Right? So this is a duplicate acknowledgement. You have already received an acknowledgement for 100. So then that tells you, okay, I sent a packet and now I'm getting a duplicate acknowledgement. So maybe something went wrong. Then you get another duplicate acknowledgement. That must mean that a new packet has been received by the receiver, but it's just not in the right sequence. Then you get another duplicate. This means that the receiver got some new data packet. It's just that not in the right sequence. So when I get 3 duplicate acknowledgements, TCP says that something has gone wrong. It must be that my packet, which started at 100, was never received. So now I don't need to wait for the timer anymore. I can directly retransmit at this point. Okay, so I don't have to wait for the timer to expire. This is what is called fast retransmit. Okay. So again, the whole idea about fast retransmit is if you get duplicate acknowledgement, so the first time you see 100, this is I expect it anyway. But the next time I see another acknowledgement for 100, it implies some packet was received by the receiver, but not what it was expecting. Then it repeats 3 times. Then I say, okay, must be something wrong, right? Now you can ask, okay, why don't I do it in the first duplicate itself? Maybe that is good enough. Yeah, maybe, but then there's also a chance that maybe it's, packets were reordered in the network and then hopefully it'll reach at some point. Why 3? Why not 10? Maybe 10 will be really, really sure that it's definitely lost, right? Even with 3 duplicate acknowledgements, it could be that the packet is just going through a very long route in the network. It's just reordering. But after a lot of years of actual practical experience, network designers realize that 3 is a good compromise. You don't want to do it at the first duplicate acknowledgement. You don't even have to wait very, very long. 3 seems to be a reasonable choice. So it's an empirical thing. There is no, theoretical proof to say 3 is the best. All right, I see that somebody has a question on the chat. Let me pick it up. So somebody is asking, is it possible for multiple retransmissions to happen within a timeout window? So the answer is, so the question is it possible for multiple fast retransmissions to happen within a timeout window? So let's say here is my timeout window. Let me get a proper color. So this is my this is my timeout window. So what I think I would probably have to redraw to answer your question, but what it means is that in this particular case, you have only one retransmission. But let me try and draw a specific case for you where this might happen. And it is actually possible to have multiple fast retransmits within the window. But in this case, what you will need is somehow the timeout value has to be really, really large. So let's take an example where that could happen. Oh, I'm using green here. It's okay. Right. So let's say this guy got through, this guy did not, and then you retransmit here, but then the timer is like this, pretty long. Let me change my colors. Now, when the acknowledgements come in, 1, 2, 3, as soon as you get your third duplicate acknowledgement, you will retransmit your lost packet. So this is a retransmission, right? Usually what will happen is when you retransmit the lost packet, you will restart your timer at this particular point. Okay, so there is always only one timer that is active, and that timer is always associated with the oldest timer value. So as soon as you do the retransmit, you have reset your timer value. So in that sense, you would not have more than one retransmission within one timer value. So after the first retransmission, now you have reset everything. And so I hope that clarifies your question. All right. Okay, so now let's get back here. So this particular slide kind of illustrates what I was talking about so far. So the timeout period can be so the timeout period can be very long. And if the timeout period is very long, we don't want to wait for the timer to expire. So it is possible to detect lost segments, and this we do via duplicate acknowledgements. So if a segment is lost, we will see that there will be multiple duplicate acknowledgements. And this is what we just saw when I was drawing out those things, right? And in TCP fast retransmit, if the sender receives 3 duplicate acknowledgements, That means you have a total of 4 acknowledgements for the same number. That kind of gives us an indication that something must have gone wrong, and then I will retransmit the oldest packet. And here's another example of the same thing. Just to reiterate, we can go through. Let's say the first packet we sent started at sequence number 92. It had 8 bytes of data. So when the acknowledgement for this comes back, it will say, okay, I've got 92 to 99, give me 100, right? And let's say then we sent 20 bytes of data that was lost. And then there was a third packet and a fourth packet and a fifth packet. Doesn't matter where they started. If they are received correctly at the receiver, the acknowledgement for that will still say, give me 100, give me 100, give me 100. And now this was the original acknowledgement, but you get 3 duplicates of this. So in total, you got 4 acknowledgements asking for the same thing. At the time, you can retransmit your lost packet. Okay, so this is the idea of fast retransmit. Okay, so now we have seen 2 things. We have looked at the segment structure, the structure of a TCP packet, and then we have also seen how TCP does reliable data transfer. So basically how TCP recovers from losses, and the way TCP recovers from losses can be in 2 ways. Either we can have a timeout, or if we get 3 duplicate acknowledgements, I can directly retransmit. So now let's look at some of the other things that TCP does, and we will first start off with flow control. Okay? So flow control is to ensure that the sender does not overwhelm the receiver. We don't want to send data at such a rate that the receiver cannot handle it, right? So if you look at the receiver side, this is what would look like. If I look at the different layers, so you have your application running here, then you have your transport layer, then you have your network layer, then you'll have your data link layer, then you'll have your physical layer, and so on. Right? And the transport layer and the application layer, when they communicate with each other, it'll be through a socket, right? And the way the socket is implemented is the operating system will set aside some portion of the memory for the 2 processes to talk to each other. So for example, when the link layer gets a new data packet, maybe I change my color here. So when the link layer gets a new data packet, it'll give it to the network layer. It'll take out the link layer headers and so on. And when the packet is the network layer, which is Internet Protocol, will then give it to the upper layer, take out the network layer headers and so on. What TCP will do is it will now do the demultiplexing. It'll figure out what is the correct socket, and now it'll transfer the data to the application. And in order to do that, the operating system sets aside some portion of the memory. TCP will write in that part of the memory, and the application will read from that part of the memory. And when the application reads, now we can free up that part of the memory. And so this is how things are working. What flow control tries to do is it tries to stop the sender from sending data too fast, such that this memory becomes full. The application is supposed to read data from the transport layer. It is supposed to read from this memory. But if you look at a typical laptop these days, you have so many different applications running. So the operating system may be busy, right? So your application may not read the data as soon as it arrives. There may be a delay, right? And if the sender keeps sending, the buffer will get full. So this is another way of looking at this buffer. So let's say this is the buffer, this is the part of the memory that has been allocated to this particular socket. When TCP gets data, it will write into this buffer. So far, let's say this part is full, and this part of the buffer is still available. So what you want to tell the sender is, you can at most send me, if this is 100 kilobytes, you should not send me more than 100 kilobytes. Right? So you have to inform the sender that maybe I had a total of 500 kilobytes. 400 of it is already used up. I only have 100 remaining. So when you send an acknowledgement back, let me draw this thing now, function W. So let's say you got some data, and this is your receiver buffer. The total size was 500 kilobytes. So you take this data, you write it in your buffer, right? And let's say so far you have already used up 300 kilobytes of your buffer. So what is remaining is 200, right? And let's say again in our example, this started at 92. It had 8 bytes of data. So when you send the acknowledgement back, these are a few of the things you will say, right? So you will say, I am acknowledging 100. Give me 100 bytes now. Also, if you go back to your the slide with the TCP packet format, you will see that there is one field, 16 bytes, 16 bits, that talk about the receiver window. And the receiver window says, I have 200 kilobytes left. So don't send me more than 200 kilobytes at this point. Okay. So let me go back to that particular slide maybe to make it clearer. Yeah, this is the slide with the TCP segment structure, and we have a receive window here. So when the acknowledgement for our example goes back, the acknowledgement number here will say 100, right? So this is again, just to recall, we got a packet starting at 92 with 8 bytes. So the acknowledgement that goes back will say, give me 100. I'm looking for 100. And this 100 is being written here. I want 100. And in the figure that I was drawing earlier, my entire buffer had 500 kilobytes, but I had used up 300 kilobytes. So 200 kilobytes were remaining. This 200 kilobytes, I'm going to write here, saying, don't send me more than 200 anymore. So the sender, when it receives this acknowledgement, it will see, okay, it's expecting byte number 100, but I should not send more than 200 kilobytes at this point. So the sender will, even if the application is giving it a lot of data, it will at most send another 200 kilobytes and not more than that. Okay. Any questions from anyone? All right. Let's go to. All right, so this is TCP flow control. So now let's come to the next section, which is connection management. So when we were talking about, when we were introducing TCP to you, we talked about how TCP is connection oriented. That means before TCP sends any data, it actually sets up a connection with, the two sides agree to exchange data with each other. And then once the data transfer is done, that connection is torn down or it's stopped. So now we will look at how TCP manages this connection. Okay. So let's say we have a client and we have a server, or we have A and B. A and B want to talk to each other. So let's say the client or A starts the connection. A wants to exchange some data with B. So initially, both of them are in what we call the state of listening. They're both waiting for something to happen. They're both waiting for somebody to start a connection with them. In this case, A decides, okay, I'm going to start the connection. The way TCP starts the connection is by using a special packet. And the special packet is called a SYN packet. And the special SYN packet looks like this. You remember our TCP packet, that the segment structure that we were looking at earlier? So it has 20 bytes of header, and then we have supposed to have data. And I guess somewhere here, port number, sequence number, somewhere here we had many different flags. One of these flags was the S bit or the SYN bit. So when I want to initially start a TCP connection, I send a special packet where, of course, the connection has not happened yet, so there is no data. So it's just a 40-byte packet with just the headers. And in the headers, the SYN bit is set equal to 1. Let me do it right. The SYN bit is set equal to 1. Also, in our examples that we have done so far, we assume that the first bit is, let's say, the sequence number will be 0, right? But in real life, even though I'm starting a new connection, the first bit does not start at 0. Instead, what we do is we randomly start off by choosing the initial sequence number. So we start off by choosing some sequence number, let's say 573. So I say the first byte I will send will be 573. So I start off by choosing some initial sequence number. And the reason we don't always start with 0 is because in some special cases, what can happen is, let's say you're opening and closing connections with the server very, very quickly. You open a connection, you close the connection. You open another connection, close the connection. So it may so happen that, some packets from a previously closed connection are still in the network. And if they reach B or the server, you don't know. Is it from an old connection or a new connection? So by randomly selecting what is the start value, you eliminate the chances of an old packet from a previously closed connection still making it to the destination, right? And sometimes it also helps with preventing, replay attacks and so on. Some cybersecurity issues also are there. So when we start up a connection, we agree on some initial sequence number. I say that, okay, I'm going to start my connection from byte number X. So byte number X is the first byte of my connection. Okay, so you say my SYN bit is 1. So if I go back again to that same particular figure with this with the segment structure, yeah. In this case, I choose some initial sequence number X. X could be whatever that you want, maybe 573. Right? And this particular SYN bit that you say is equal to 1. And only these 40 bytes are sent. If you want to send optional, that's okay. But in general, only the first 5 lines here will be sent. There is no data here. The connection has not been set up yet. Okay, so you now send this first packet with a sequence number of X and the SYN bit set to 1. When the server received this, let me erase this. When the server receives this particular packet, it realizes that somebody is trying to open a connection with me. What should I do? You have two choices. Either you can accept or you can reject. But you're a server, so hopefully you will accept this particular connection. So when you accept this connection, your state changes from you were earlier listening, waiting for a connection to come in. Now you got a request for opening a connection. Now your state changes to SYN received. You received a packet with the SYN bit set to 1. And on the client side, initially we were just waiting, but now I have sent a SYN, so my state changes to this. So since the server is willing to accept the connection, let's say, what it will do is two things. First thing is it will acknowledge. It will say, okay, I have received your SYN connection. So I'm acknowledging it. So in that packet, the ACK bit is set to 1, saying, okay, I'm acknowledging you. And I understand that you want to start the connection at X. You already sent me the SYN packet, so I count it as the first thing. So now I want X plus 1 from you. So this is accepting the fact that this client can now send data to me. So it has opened this direction of communication. So the client can send to the server. But TCP is full duplex. Both sides can send to each other. So the server may also want to send data to the other side. So in order to open the other direction, it also says, I also want to open a connection with you. So it sends the SYN bit also to be 1. And since the server can send data, what will be the initial sequence number? The server says, I'm going to begin with some random number Y. You started at 576, maybe. Let's say X was 576. I will start at 12,523. Something I choose at random. Okay. So what this will do is two things. It is acknowledging the SYN that was received and say, okay, your side of the connection is open. You can send me data now. But I also want to send data to you. This is a full duplex thing. So here is me requesting a connection with you. So I also want to synchronize with you. SYN stands for synchronize. And when I send data, I'm beginning at Y. So now when this particular packet comes in, so now if I go back to my segment 1 there. Yep, here. So now two things. The acknowledgement is set to 1, so I'm acknowledging you. And here, the acknowledgement number will be X plus 1, saying I have received your request. So now give me X plus 1. I also want to initiate a connection with you. So this SYN is 1. And I am starting at Y. So next time I send you something, it'll be Y plus 1. Okay, so the message that comes back from the server has more things. So the SYN is 1, the ACK bit is 1, acknowledges X plus 1, and it also says I'm going to start at Y. All right. So now let's go back to our handshake thing here. All right. When this packet is received at the client receives this. It understands that the other side is acknowledging my X. Now it's looking for X plus 1. That means the connection has been established. But the other side also requests its part of the connection to be open, right? So that's why it was sending a SYN bit of 1, and it's saying that I'm going to start at Y. So you also want to allow the server to send data to you. So then you reply back saying, hey, I'm acknowledging you, and I know that you wanted to start at y, so now give me y plus 1. Once this third packet is received at the server also realizes that the connection has been established. So after this exchange of 3 packets, both sides have opened connections with each other. So now this guy can send data as well as this guy can send data to this side. And since there are 3 packets involved, we call it a 3-way handshake. By the way, one thing, maybe a little bit more of details here. Let me go back. Let's say the client sent the SYN packet, got a response back. If you look at this response, there are 2 things here. There's a SYN, there's also an ACK. So there's a special name for this packet. This is called a SYN-ACK packet, right? But anyway, let me come back to what I want to say. So once this SYN-ACK packet is received at the receiver, at the client knows 2 things. It knows that its original SYN is being acknowledged here. That means I can send data in this direction. I can already send data. Also, the other side also wants to send data to me. It's also trying to open a connection. So let's say ACK bit in the flag. I'm going to set that to 1. And the ACK num will be y plus 1, right? But what if I already had data to send at this point? I don't have to wait for a later amount of time. My connection in this direction is already open. So along with it, I can also send data. So the third packet which is sent does not have to be just a 40-byte packet. If you want, you can also include the data. If the client wants, the client can also include data along with the whole thing. Okay. So in most real life cases, what will happen is the first 2 ones will be just 40 bytes, just the header. The third one, of course, it will have some, ACK bit and ACK num plus 1, which will say y plus 1. But you can also, at the same time, piggyback data to it, just to make life a bit more efficient. Any questions on the 3-way handshake? All right. So this is how you open a connection. What about closing a connection? So again, after you have transmitted all your data, you just don't hang up. You do something gracefully. You tell the other side, you inform the other side that the connection is over. Now we want to close the connection. So just like you had a 3-way handshake here to close the connection, you also have an exchange of messages to close the connection. And in this case, for setting up the connection, we use the SYN bit in the flag. For closing the connection, we use the FIN bit in the flag. So let me go back here again to the TCP segment structure. So for setting up the connection, maybe I'll use green here. For setting up the connection, we were using the SYN bit. But for closing the connection, we use the F, the FIN bit. So if I want to close the connection with the other side, I set this to be equal to 1. Right? So now let's look at how the TCP connection close happens. Oops, sorry, I went too far. Okay. So right now, let's say the connection was established. So both sides were exchanging data with each other. So now let's say the client says, I'm done with sending data. I don't want to send any more data. So what it is going to do is it's going to send a special packet with the fin bit set to be 1. And this is the sequence number right now. This X is different from the the X we used during connection setup. So this X is so far, what is the sequence number after all the exchange of the data? So right now, the current base is at X. So I say up to X has been sent. So I send a fin bit, and this is the current sequence number. When the server receives this packet, it acknowledges it. So the ACK flag is set to 1, and the acknowledgement number says, okay, you sent me a fin packet with sequence number X. The way I acknowledge it, I say, okay, now I'm expecting X plus 1. Of course, I know that you will not be sending me anything, but this X plus 1 is just to indicate that we have received your fin bit. At this time, this direction of the pipe is closed. The client can no longer send any data. But this direction of the pipe is still open. If the server wants, the server can still send data. And then the client is, when it sent the fin bit, it entered a state called fin wait 1. When it gets the acknowledgement, it enters a state called fin wait 2. That means, okay, my side of the connection is closed. Now I wait for the other side to close its connection. If the other side wants, it can keep sending data, and you will keep sending acknowledgements. The other side can, as long as it wants, it can keep sending data. And for every data that is sent, you keep sending acknowledgements. But you cannot send any data anymore. This is not allowed. Data in this direction is not allowed. You have already decided to close your connection. At some point, the other side will say, all right, fine. I am also done with my side of the connection. So this guy will now send you a packet with the fin bit set to 1. And let's say currently the sequence number is Y. Okay. So now the client also realizes, oh, the other side wants to close the connection. So let me acknowledge it. So you say, okay, you set the ACK flag to be 1. And you say, okay, you last time sent a fin bit, and at that time the sequence number was 1. I'm acknowledging it by saying, okay, give me Y plus 1. I know you will not give me Y plus 1, you're closing it, but it is Y plus 1 just because I'm acknowledging your fin bit. Right? Once the server gets this, it knows that the connection is closed. Previously, I have acknowledged this side to be closed, and now I got the acknowledgement for the other side closing my direction of the connection. So the server is done. But if you look at the client side, at this point, we got the fin request and we replied to the fin request. But I don't close the connection yet. I wait for some amount of time. This is usually 500 milliseconds or 1 second or 2 seconds, some amount of time we wait. Why? The reason we wait is, yeah, I got the fin bit and I acknowledged it. What if this was lost in the network? What if my acknowledgement is lost by the network? Then the server will still wait. The server will time out at some point. There'll be a timer. When the server times out, it's going to send the same fin packet again. And if I close my window, if I say this is closed already, I'm not going to reply to this, right? So this is not going to happen. and then the server will keep retransmitting again and again and again. So we don't want that to happen. So to allow for the cases that, it is possible that my ACK can get lost and there'll be a retransmission of the FIN request from this side, I still keep my connection open for some amount of time. If I don't get another FIN request from the other side in this window of time, then I realize, okay, everything went correctly, and so on, and then I can close. Okay. Any questions? No? All right, so let me look. So my clock says, well, it's evening here in California. It's 7:30, but I guess it's 11:30 or 11:27. So maybe this is a good time for us to stop here today. So on Friday, we will meet in person, and we will meet in LT3. So when we come back on Friday in person, we will talk about TCP congestion control, and hopefully we will be done with TCP on Friday. Okay, so we'll stop here for today, and I'll see you all in person on Friday.